Oleksandr Gurbych. He has a PhD in data science and is CEO of Blackstar.ai. Very passionate guy who always talk at our conference about applying data science to interesting models, especially in chemics and biology. I think Oleksandr will tell more about himself by himself. And let me pass to Oleksandr. Oleksandr, go ahead. Time is yours.
Thank you, Ross. Hi, everybody. Good time of the day. Thank you for introduction. Today, I'm going to talk about one of the applications of AI in a little bit unusual field. It's intersection of chemistry and math and AI. Somebody calls it cheminformatics. And it's about deep learning for chemical reaction screening, as you see from the first slide. And particularly, it's applied to prediction of a chemical yield. So I believe you all, to some extent, studied chemistry in school or university, and probably know something about chemical reactions and a couple of descriptors which help us to understand them better. You should probably know that there are reagents and reactants and products of reactions, and chemists perform this reaction because they want more of a product using less of reagents and reactants. And this number, which shows us the relation of amount of desired product obtained divided by the reagents and reactants we've spent for this reaction, is actually chemical yield. It's a real or actual chemical yield. And you see, this is in simple words, it's a number in this red rectangle. It shows us the percentage of a reactant converted to the product. And logically, you can conclude that the larger this number, the better way of a reaction we can choose, especially if we can compute this number in advance, not by running multiple trials just to understand good or bad pathways of a reaction. So this is a task of today's speech. I will talk about how we can use AI tech to predict this number without losing any reagents and spending time in the lab trying this and that to get more of a desired product. So the core model we've developed and used is DMPNN, which is a deep message passing neural network. Just from the name, you can conclude that it passes messages. And first of all, it's a graph neural network. And secondly, it's a recurrent graph neural network because there are convolutional and recurrent ones. Recurrent means that it works like backward, multiple cycles, and passes messages from one cycle to another. So it recursively goes from the neighboring atoms and bonds to the target atom and bond, and do this for all atoms and bonds in molecule. Here is I'll just briefly describe the technology. I'm not going deep into it because it's a separate topic. You should probably know about neural networks and vectors and parameters and features and all the stuff. If not, please write it in the chat. I'll drop you some books or links which will be useful for you. So what happens here? Imagine we want to, so first of all, there are two kinds of features. First are bond features, which describe some chemical bond properties. And which chemical bond properties do you know? Can anyone give an example? Rostislav said me that here we have chat. Feel free to, I don't know, write anything in the chat. Okay, if not, I'll just give you a couple of examples, ideas. Chemical bond features might be the length of the bonds, the energy of a bond, the multiplicity of a bond, because there might be singular, double, and triple bonds, and also aromatic bonds, etc., etc., etc. So there are a set of chemical properties which describe chemical bonds. And all these properties is depicted here as these dots. And these features all combine in a vector, and we pass this vector from bond to bond, following like the sequence of bonds up to the desired one. So if we are computing bonds for atom number 1, we first go to, bond 2 to 1. We first go to bond 3 to 2, then to 4 to 2, then to 5 to 1, and combine all the features, and concatenate them, do some averaging, blah, 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 and compute a vector for desired bond 2 to 1. That's how it works. Then we go to the neighbors of the neighbors, and you know how recursion works. It is about bonds. What about atoms? The second entity of chemical molecules are atoms. And atoms are treated as nodes in the graph, comparing to edges bonds. And there are the same, not the same, but a set of features, atom-specific features. For example, we can give such features as valency, number of electron on the latest electronic layer, molecular weight, and others. There are tens of them. And again, they are combined in a vector as in previous case. And what you do with them, the same thing as with bonds. You simply, if you want to compute the atom vector for atom number 12, which is carbon, you go to all its neighbors, to nitrogen number 5, carbon number 13, aromatic carbon number 17. You combine their vectors, like shown here, sum them, and then it will be the new atom vector, concatenate with the previous values of carbon number 12, and then do some magic, and you receive new carbon 12 feature vector. And now imagine we combine two that capabilities into one neural network. And here you go, it's a DMPNN. So it's a message passing network to sum up. And it passes information about nodes or atoms and edges or bonds in a molecule. Why we chose this model? Because it's naturally very similar and perfect mathematical model for molecules. Because chemical molecules, chemical structures, they all essentially graphs. And if you take a graph neural network, which models edges and bonds and atoms as edges and nodes, you can expect that the mathematical model will be correct at some point, at least, because the nature of math and nature of nature itself, they are very similar. So I hope you understood something about graph neural networks and DMPNN in particular. If not, it's time to ask questions. Yeah, please.
Okay, does anybody have a question about graph neural networks or about the whole idea of applying?
Okay, I hope yes. I'll repeat it in short terms. Whole idea is to model the nature of a chemical molecule, which is essentially a graph, with a mathematical graph, which has values for each atom and each bond. And we hope that this stuff will describe the reality as good as it is possible. It was a core model of our research, which we applied to this yield prediction, and how I will tell you just in a second. Okay, I'll continue. So imagine you have this DMPNN, which works with atoms and bonds. And now it's original picture from our publication, which is pending in one of the peer-reviewed journals. Here, the reactant 1, reactant 2, and products, they all featurized as graphs and passed to the direct message DMPNN, essentially. So that each atom and each bond is parameterized with vectors of feature values. But what's next? Next, we're interested not in the reactants and products themselves, but we are interested in the reaction. What has happened with those atoms? And we all know the law of mass and energy saving, that the mass do not disappear simply, and the energy do not disappear, they just transform. And for chemists, the mass saving law says that the same amount of atoms which participate in, which started reaction, they later can be found in the products of a reaction. So atoms do not disappear anywhere, they just regroup. That's the essence of any chemical reaction. And using this law, we decided that the most sense of this chemical transformation is not about the molecules themselves, but rather in a difference, what has changed in terms of a structure or bonds and atom regrouping or atoms, positions of atoms. And we compute that separately. First, we compute what has happened with bonds. We like map state of bonds here and state of bonds here. And this set of vectors mirrors that. And the same we do for atoms. We show which atoms from here moved to which position in a product. And this atom replacement is parameterized with a different fingerprints for atoms. So imagine after transforming the reactants and products into graphs, we compute them. We compute we map how atoms moved and how bonds changed. And that's the essence of a transformation. And we use this as input to another DMPNN. And that another DMPNN outputs a smaller vector, which we call reaction encoding. And at this stage, we add more parameters, like some atoms do not participate in reaction, but they play an important role in reaction itself, like catalysts and some subproducts and some defense groups or exiting groups. Well, that's a chemical terminology. Just take a note that we add more information here. So we've got some reaction encoding, which is a representation of changes which happened in that type of a reaction. And then we add some more information in the form of some matrix. And we put all of that into a multi-layer perceptron, and we feed to a desired label, which is a yield of a reaction. It's a percentage of outcome of a reaction. That was the core of this research, the core idea and the core algorithm, which we used. And next, I will show you different plots, results, distributions, etc. But it's a moment to ask questions about the technology itself, if you want, if you're interested. So please.
You could write your question in the chat if you want, or just wait till the end of the presentation and ask them by voice, at your choice.
Okay, later I will publish it on a YouTube or something like that, and you'll be able to ask questions in the comments. Also, maybe I'll notify when the paper will be published. Okay, let's continue. So then there were two sets of data. First is a single reaction data, it means that there are hundreds of thousands of rows, but the underlying mechanism of a reaction was the same for all of the rows. We call that single reaction class. And there were two mechanisms underlying, and appropriately two data sets separate. Suzuki-Miura, which is CN cross-coupling, very popular in chemistry, and Buchwald-Hartig, which is one of the amination reaction. And the unique feature of our research was that we had some proprietary private top secret data set, which one of the chemical providers shared with us. It was deeply experimental and their own property. The company is called Yenemin. They do organic synthesis of different compounds, which they later sell. And those data set consisted of 10 reaction classes. Why we separated that? Because after literature review, I realized that the attempt to fit multiple reaction classes is a much harder task than fitting single reaction class. Maybe it is due to some chemical nature, because from the same mechanism, you can expect that the same inputs gave you the same outputs, slightly different number of carbons or nitrogens or etc. But the nature of a transformation is always the same. That is why it's called the mechanism. And for multiple reaction classes, we can expect that there will be multiple such mechanisms. And that's why the nature of these different fingerprints, they will be completely different, and it will be much harder for any model to fit that. So here is a brief schemas of our single reaction class data sets. Now I'm going to describe the results which we achieved on a first single reaction data sets and then on a multiple reaction data sets. Again, as a typical data science machine learning task, we plotted distributions of a data, and pay attention that on the y-axis, here we have number of samples, the number of reactions for particular yield percentage, and here yield represented in percents. Here is a schema of a reaction. I don't know, if you don't love chemistry, maybe I shouldn't go deep into details, but the idea of this reaction is that radical 1 finally at the end combines with the radical 2. You see this product, and these two groups, Vy and X, they are lost, they are exiting groups. And in Buchwald-Hartig amination, we aminate aromatic compounds. So imagine you have an aromatic compound with some substituent, and then you have secondary amino group here, and it just joins to this aroma group. That's not essential, but anyway, the nature of reactions is a bit different. So what did we get? First of all, we benchmarked multiple ML models just to give us some feeling. We wanted to take some baseline and then beat it with DMPNN, and we took FCNN, but then very competing and very high level good model, which is BERT. It works completely different. It's a transformer, you probably know. It works on a pure textual representation of a reaction schemas without any parameterization, graphs, features at all. You simply like give to it reactions as a text, and it fits something. And sometimes it works as good as our model, or even better, slightly better in some cases. Yeah, but anyway, we achieved very good results from the first attempt. And that's on the single reaction data sets. To the left, you see on the Suzuki-Miura, and to the right, it's a Buchwald-Hartig. Yeah, and these numbers as a result of a 5-fold cross-validation, everything according to best practices in machine learning. Any questions to that?
It's look pretty simple and pretty straightforward. So, but if
others are sleeping, probably raise your hand if you want to go home or cry.
Others, please put plus in the chat if you hear us, and if you are interested. If you are not sleeping, put minus if you are sleeping, and and not.
Okay, yeah, that's a joke.
Yeah.
Don't take it personally. I'm just trying to do a pause
to warm a little bit.
Yeah, hard to accept to take so much information condensed in such a small amount of time. Let's continue. So second, we took these multiple reaction classes. I'm not explaining what kind of reaction, just believe me, they are like 95% what happens in industry for organic chemists. I know these guys personally. I talked to them. They said that this data set represents what they do 90% of time. It's 95% of their business. And well, if we are able to fit it, that will be of a huge value for them. So it's alkylations, condensations, acylations, couplings, and other types of chemical reactions. The idea here is the data itself much more complex than in previous case. And here is a bit more insight into data. So the data was, in this case, was classified into 2 labels. First is a class label. The class label was low, zero, medium, or high yield. High yield, and you see the distribution here. Zero yield means that the reaction doesn't go. Low yield means that it yields in something up to 20%. Medium yield is something between 20 and 60, and high is everything above 60%. The second label was a continuous label. It was a yield percent of a reaction. And you see that there are a slightly bit larger amount of low yielding reactions and less medium, and the smallest fraction with a high yielding reaction. Also, at the bottom, you see the split based on a zero, the same, but per reaction class. As you remember, there were 10 reaction classes, and we split the samples, the number of samples per each reaction class. So the bar, the height of a bar corresponds to the number of samples of a particular yield class within each reaction class. And you see that the data is disbalanced. And what we do with this balanced data, okay, we either use weighting or specific losses like focal loss, or we try to equalize the amounts of samples in each class by upsampling or downsampling. That's like 4 basic, probably primitive techniques to deal with data imbalance, which we applied to this problem, and we used upsampling and augmentation. And here is the results. Again, our model was the best among others in almost all cases. It was, but first, I decided to separate this not occurring reactions with the zero yield, because they should be different from others. And we first performed a binary classification into reaction and no reaction. And later we split reaction into multiple classes, and low, medium, high, and regression in a percent. Next, we calculated accuracy per reaction class because we would like to know, is there any difference or does our model skewed towards any class, or is it generalized as well across all the classes? So we computed accuracy per class, and we see that our model is pink, DMPNN. It has like also highest accuracies among all the particular classes, and we do not drop out of, like it's always 65, 75%, which is good. Anyway, I forgot to mention that the benchmark, the previous benchmark, the previous published paper, it was published in Nature, and guys there achieved 65% of accuracy on just 2 reaction classes, and we achieved like 70 on 2 classes. We achieved 70, which is 5% more, and on multi-class we achieved 51% per class, which they never did. Here is the error analysis. Again, we've used multiple models for a baseline, like logistic regression, SVM, CatBoost, BERT, and then our model. And we analyzed how many reactions mistakenly classified there were per each class, and the height of this bars correspond to the number of mistakenly classified samples. And the color of the bar subparts corresponds to the particular yield class samples which were incorrectly classified. Next, we tested how our DMPNN model works when we train it not on all 10 reactions, but when we train it on 9 reactions and leave the 10s for the test set. So we moved all the samples from the reaction mechanism number 10, for example, and we did the same for every reaction class. We took reaction mechanism 1, for example, and moved it to the test set, and then trained our model on mechanisms number 2 to 10, and studied how the model just learns the typical pattern of a transformation. Does it generalize across different reaction classes? And it appears that yes, to some extent, it generalizes. If you recall, there were 0.51 accuracy average across all classes, and from like 60 to 75 for one reaction class. Yeah, and here we see the same. It is somewhere between 0.6 and 0.75. Sometimes it drops a little bit lower, like 0.4 and 0.4. Yeah, but in general, it works. The model is capable of generalizing across reaction classes, which were interesting. And here, it's an interesting plot. What we did here, as you remember, there were 2 DMPNNs, and the first model was a multilayer perceptron. And we took this DMPNN, extracted the final layer of weights, which is located right prior to the prediction layer, and we clustered the weights. And we learned which neurons are activated when the samples of a particular reactions are classified. So we took all the samples of reaction 1, put it to our neural network, learned which neurons are activated, and we did the same for all the reaction classes, and we learned the activation pattern of this layer. And then we saved this layer, exported them, and clustered. Here you see the clusterization of weight activation, right, of a final layer, and you see that it clusters into particular mechanism classes. You see that maybe not super clear here, but the 10 mechanisms are visible here, and they are painted in different colors. So the result is the neural network, DMPNN, were able to some extent, which is higher than all existing works. It was able to classify yield and as a regression and as a classification. And we see that it was not by accident, but rather the weights corresponding to the prediction. And here is the team which does this work. It's Dvinka Jarish, Sofia Garkat, and me. So thank you for attention. I'm open to your questions. Again, I'll remind you that this topic relates to chem informatics. It's a bit unusual for machine learning community because we've used tasks like finance, banking, insurance, I don't know, image classification, etc., etc. But there are more interesting fields, as I think, which bioinformatics like and chem informatics and precision medicine and genetics, and like we work with that.
Great. Does anybody has questions about Oleksandr's talk? You could write it in the chat. Or you could ask them by voice. Let me check other links. Not in the Telegram chat and not in the broadcasting chat, not yet. Yeah, thank you, Oleksandr. It was very impressive work. Yeah, a lot of information. I try to follow. Yeah, it really requires some time to think about and to understand. But I think it's a great work. When would be your paper published?
I think in a month or so, because it takes some time for the reviewers to check it. Then they provide the feedback to you. Then you probably fix some things, and then you send it back, and then it is published in a week or so. But all this process takes is a month also.
Please, if it's open journal, please send us links, and we will send it to our participants to give them better understanding of your work and what you achieved. And probably paired with this video, it would be more explainable and more understandable for everybody.
Thank you. I'll be delighted to.
Okay, everybody, let's thanks to Oleksandr. You could use signs like that or like that to thank Oleksandr for his presentation.
Thank you for your attention and for your time again.